So you'll see at the very beginning that, that says operator, and that we have the longest title of any presentation today, and I'm not going to repeat it. So we're going to get into the fun stuff here. So Alex and I are senior lead software engineers at Capital One. We build machine learning platforms. We've been doing that for a while, probably too long. We're both SRE adjacent, but we work across the board. And what we currently run at Capital One serves data scientists, machine learning engineers, and business analysts across the company. We've got 51,000 employees at Capital One, and we serve a pretty solid subset of that. And our platform enables a ton of work. So our talk today is going to focus on a very small subset of that, which is Jupyter notebooks and tooling that's commonly used in ML across our lifecycle. As a joke slide here with it being black, in the beginning there was darkness, and it wasn't hard servers or bare metal like there was in other slides. It was Excel and spreadsheets, and it still is in some cases. The first rays of light in interactive analysis in the field came with Mathematica in the 80s. There was a guy named Theodore Gray who designed the first interactive notebook for that ecosystem. And in Python, dawn blossomed with IPython in 2011 as IPython notebooks for an interactive REPL showed up. And then in 2014, the Jupyter project was launched into the open source, and there was much rejoicing. So what's Jupyter and why does this matter? Well, trivia here, its name is a mashup of Julia, Python, and R. They were the 3 original languages that were supported. It's now across 40 different programming languages in modules and extensions. And what this is it's an interactive web-based UI, and you can either run it in a local web server in the original design, or it's containerized on a variety of platforms for service. We run it on basic Kubernetes. In hyperscale clouds, you can find these things underpinning stuff like AWS SageMaker, GCP's Colab for a couple of prominent examples. If you're an SRE by trade, well, you may never have used one, and that's okay. We're going to kind of dig in to the interesting nuts and bolts of the Jupyter service backend. And there's a lot of lessons across the board here. So backing up a little bit, this is what a machine learning lifecycle looks like, and our work encompasses the technical parts of that. AWS looks at it this way through their well-architected framework. If you're in ML, there's a lot of opinions on what this is. Solutions that we've constructed in the past based on this diagram kind of fit between data processing, model development, deployment, and monitoring. We kind of work across all of the technical pieces of what it takes to get models built and deployed. And even though Gen AI is starting to interfere with our work, it's no less true in the LLM space as it is in the traditional machine learning space. So what we're going to look at today is Jupyter notebooks. So that fits into data processing and model development primarily. Common tasks that you might see a data scientist or a data engineer or a business analyst, for that matter, do here would be things like data exploration, munging, cleaning, feature engineering, model prototyping and model training take a lot of our time, and then validation and shadow scoring, among other things, model-centric. Inference is pretty split due to business rules at Capital One. So especially for our platforms and in this space, it is primarily on the pre-inference or pre-production side of model training. Generative AI and prompt engineering can live here too. So if you work in the data engineering space or you have workloads that run in there, you can see this for stuff like prototyping transformations to orchestrated DAGs, Airflow, Prefect, some other tooling you may be familiar with, or you may at least have heard of across that area of your company. So at so Jupyter Hub is the first thing we're going to talk about. This is what we started with at Capital One for provisioning notebooks. It's self-described. It's a multi-user version of the notebook designed for companies, classrooms, and research labs. It's a backend agnostic, no provisioner and traffic router, and it's got nice bits like authentication built in. So once a Jupyter notebook user graduates from their local machine and starts needing workloads larger than a single endpoint or GPU support in a lot of cases, these days they go to Jupyter Hub first if they're self-hosting this type of thing. When we adopted it a few years ago before the 1.0 release, Jupyter Hub was stable and it met all of our initial use cases. but it turned out to be challenging enough to maintain in a large environment that by the time we scoped it up and we scaled it up, we were already looking to make changes due to issues with availability and not meeting our SLA and SLOs on the platform. So now that I've mentioned SLAs and SLOs, we've fulfilled our contractual obligations for speaking at SREcon. So the basic theory of operations is this. The hub creates a proxy for Jupyter Hub. That's one pod. The proxy forwards all requests to the hub by default. And the hub handles logs and spawns single-user Jupyter Notebook servers on demand. And in this Kubernetes-centric diagram, they're represented by pods and volumes. The hub then configures the proxy to forward URL prefixes to the single-user notebook servers for user connections. And that's how a user in a container environment gets that URL back that they can work from. There's a database that backs this. Generally, it gets put on a PVC and an EBS volume in an AWS environment. And that's directly attached to the system and not in a managed database. This tends to work pretty well in normal operations, but if you know anything about how EBS volumes transit between AZs and different nodes in a Kubernetes cluster, you may imagine that this may cause issues in some cases. There's a couple other lower level features worth pointing out as nice to haves here. In Jupyter Hub, status logs are available before the notebook servers come up and are exposed via WebSocket and streamed real time to the UI, so that a user can get a good view of what's going on while their server provisions. That has been a really nice thing for UX on our system. Also, the underlying hub config is readable, pure Python, and easy to extend under the hood in cases where custom options are required. So that's a good overview of Jupyter Hub, and now that we've provided a high-level overview, I'm going to hand it off to Alex to talk about Kubeflow and the Kubernetes side.
Thanks, David. Hi, everybody. It's nice to be in a room full of people who actually care about what we do. If you haven't seen the latest Krasiam video, which is called Positive Affirmations for SREs, I highly recommend it. So one of them is, your friends and family understand what you do. No, they don't. In their defense, I kind of don't either. So let's talk about Kubeflow. So Kubeflow is a machine learning toolkit for Kubernetes. Many different tools are used in the model development lifecycle, and Kubeflow is fairly unique in its efforts to kind of consolidate a broad suite of otherwise disparate tools under a unified platform and a unified interface. The individual tools within the suite tend to be very narrowly focused on particular problem domains, and when you move from one tool to another as you progress through the model development lifecycle, it can be challenging and sometimes be an inconsistent experience. With its consolidated interface and powerful workflow orchestration capabilities, Kubeflow closes those gaps and makes using otherwise disconnected tools much easier. So today we're going to focus on a very small subset of what Kubeflow is capable of, namely notebook provisioning, obviously, because we're comparing and contrasting it to Jupyter Hub. So to solve for notebook provisioning, Kubeflow implements a Kubernetes operator. In a nutshell, operators consist of one or more custom resource definitions, which provide a new data model and extend the Kubernetes API, as well as a controller application that responds to, among other things, the creation of corresponding custom resources. That's quite a mouthful right there. It's hard to summarize operators in a single paragraph. So control loops are kind of at the heart of what powers Kubernetes. Fundamentally, the reconciliation logic compares desired state as defined by a combination of the custom resource that triggers the reconciliation loop and logic within the reconciliation loop. And so it compares that desired state with actual state, which typically, but not necessarily, is what's actually deployed on the cluster. And when it identifies a discrepancy, it reconciles the two. That's why it's called a reconciliation loop. So yeah, now that we've talked about operators in general, let's talk about the Kubeflow Notebook operator specifically. Essentially, it extends the Kubernetes API with a new model called a notebook. When a new notebook custom resource is created by a user, typically through the Kubeflow UI, although you can call the Kubernetes API to create it directly, the notebook controller's reconciliation loop activates, calls the Kubernetes API, and then creates three resources: a stateful set, a service, and an Istio virtual service. These three Kubernetes objects, two of them are, I guess, are vanilla objects, and one of them is a CR in its own right, in concert are able to run and serve a notebook server. Thus, desired state, a functioning Jupyter notebook server, although not necessarily just Jupyter, and actual state are brought into alignment. All this happens almost instantaneously, and the average data scientist is mercifully oblivious to the implementation details. Did you hear the joke about the data scientist with deep Kubernetes knowledge? Never mind, it's too unicorny. This is the part where you're supposed to laugh. So actually, once upon a time, Kubeflow used Jupyter Hub for notebook provisioning, and then they switched. And much of the rationale for that switch is documented in this issue, which I've linked here. We'll share the deck, obviously. In the next few slides, we're going to review that rationale and use it as a lens to compare and contrast the two solutions. A brief disclaimer before I go on. We use both products. Each product has its pros and its cons. This is a comparison. We're not trying to disparage either of them. So instead of relying on etcd as the source of truth, the Jupyter Hub's central hub component maintains its own database. David alluded to that with the EBS volume. To quote one of the maintainers, the hub itself is a single point of failure and must own the database it talks to. Other hub instances may not be running and talking to the same database, or there will be errors and inconsistent state. So you cannot easily have two hub replicas and failover between them. It's the kind of thing that gives SREs nightmares. If the hub crashes or is evicted itself, the service goes down for minutes at a time. I love this comic. David pointed it out to me. It's so accurate. So in contrast, because the Kubeflow Notebook operator is Kubernetes native, its only data store is the Kubernetes database, which is almost always etcd, a distributed reliable key value store that uses the Raft algorithm to achieve consistency and high availability. I kind of assume everybody in this room knows what etcd is, but whatever. Unlike the Hub API, the Kubernetes API is highly available. There can and typically should be more than one Kubernetes API replica at any given time. And these replicas can receive requests and interact with etcd in parallel, thanks to etcd's sophisticated data model. Moving on to auth. So Jupyter Hub is a solution to one problem, notebook provisioning. It therefore provides auth for one problem, notebook provisioning. Its auth implementation is really impressively extensible, but it's nevertheless single purpose. In contrast, Kubeflow is a solution for many problems, notebook provisioning, workflow orchestration, hyperparameter tuning, et cetera. Kubeflow provides highly scalable and decomposable auth for many problems thanks to Istio, which we'll come back to in a second. And Kubeflow also leverages Kubernetes RBAC and all of its corresponding benefits and flexibility. So by default, Jupyter Hub ships with something called configurable HTTP proxy, which I will now refer to as CHP because I don't like product names that are tongue twisters. The hub spawns CHP and configures CHP's routing table to forward URL prefixes to notebook servers. CHP is a single point of failure that can be scaled up but not out. In addition, if CHP goes down, much like Hub, it can take time to come back online. And that's because it takes a while for the hub to reconstruct CHP's routing table, which defaults to being stored in memory unless you specify an external storage backend, such as Redis. Jupyter Hub eventually released a traffic-based proxy, which significantly improves high availability, but that was long after Kubeflow had finished migrating to the notebook operator. And really by migrating, I mean building. So instead of CHP, Kubeflow uses Istio, which is a Kubernetes-native service mesh that lets you transparently add capabilities like observability, traffic management, and security without having to implement them in your code. Istio includes a data plane, which consists of either proxy sidecars or proxy daemon sets, depending on whether or not you're using ambient mesh, which you should be, and a control plane, which manages and configures the proxies. Istio relies on the Kubernetes database as its data store. So all of the benefits that we discussed about etcd are leveraged by Istio as well. Unlike CHP, Istio is highly available and resilient. So let's compare the UIs now. The Jupyter Hub UI is Spartan, but it's very extensible. You can control the notebook configuration form using Python and deploy it without modifying the underlying image, since the hub can load the code dynamically at runtime. It's actually a really great developer experience that I wish more products replicated. In general, Jupyter Hub's extensibility across the board is one of its most compelling features. In contrast, the Kubeflow Notebook UI is extremely feature-rich and polished. It puts a lot more control in the hands of end users by default. You can provision multiple persistent volume claims, specify storage classes, storage size, tolerations, affinities, as well as pod defaults, which are kind of a Kubeflow notebook-specific thing that uses dynamic admission control and mutating webhooks to essentially kind of sideload additional functionality. it would take a tremendous level of effort to replicate this functionality within Jupyter Hub. So in Jupyter Hub's defense, to quote one of the maintainers from the aforementioned issue, is it aforementioned, aforementioned? I never know how to pronounce that word. The target use case was a single machine with 5 to 50 users, and several design decisions were taken with user space, installability, maintainability, and simplicity in mind, while scalability was explicitly out of scope as something we knew we didn't have the resources to tackle. At the end of the day, Jupyter Hub targets many different backends with backend-specific spawners, not just Kubernetes. These spawners include Docker spawner, sudo spawner, batch spawner, yarn spawner, SSH spawner, and obviously kube spawner, which we've been talking about this whole time. If you want to provision notebooks in a local high-performance computing context, Jupyter Hub might be a better fit than Kubeflow notebooks. When we're talking about Kubernetes, though, it's a different story. I'm now going to hand it back to David to talk about lessons learned from using both solutions.
All right, so as you've seen, this comparison is a specific example of the, hold on just a second. There we go. I forgot I had to click on the last slide to get the titles to come up. This comparison is a specific example of the broader principle that backend agnosticism can come at a price. Jupyter Hub is remarkably flexible. It can go across a variety of different spawners, and it can handle significant running volume of notebooks on a Kubernetes cluster. But in our experience, we were able to handle many, many more concurrent notebook provisions with Kubeflow and Kubernetes without experiencing controller crashes. In some cases, up to 10 times as many during load testing, not even just a small fraction there. If you know you want to provision notebooks on Kubernetes specifically, our recommendation in this case is to use Kubeflow. Second, when you're trying to solve an ecosystem problem, you need modular, decomposable, shareable, and independently scalable components at scale. Self-contained solutions can be incompatible with a broader ecosystem-focused approach as system sizes grow. This is seen in the traditional monolith versus microservice conversation and also here. Third, there's always a trade-off, again, with a monolith versus microservices and similar in Kubernetes. Scalability and resilience bubble up when you build on top of distributed first architecture. It's much easier to reach high availability. Despite being heavily invested in Jupyter Hub at the time, the third one here is to avoid sunk costs. Kubeflow made the bold decision to pivot. In our opinion, it was the right choice, and we had to also make that decision when we moved over. Sometimes you have to take larger measures against tech debt when problems are realized that can't be dealt with by patches. And finally, the saying goes, there's no such thing as perfect architectural choices, just progressively less bad ones. Even some of the truths that we hold self-evidence, like the rightness of the Linux, Unix, small command line tools construction, are just very good, but can't be considered perfect in every case. There's still people trapped in VI trying to get out. Both of these notebook provisioners are evolving, as is our decision-making around what the optimal tooling are for problems that we're solving. There may eventually be another one that surpasses both of them, and then all we can do as engineers is make the best decision that we can at the point in time with the information available to us. Wow, a lot of material for a little over 15 minutes. We hope everybody is still awake dealing with this topic. That concludes our presentation. Thank you for participating, and hopefully we've got a minute or so for QA, and if not, we'll take questions on Slack.